In this video, we are going to learn how to segregate a sound into its different acoustic components. For that purpose, we are going to use a library, Librosa. So let us see which version of Librosa we are using. We are using 0.8.1 version. So first what we are going to do is we are going to download some of the audio example on which we are going to work. So we are going to work on one of the example, which is Nutcracker, and this is a syntax through which it can be downloaded. So once we have downloaded the signal, let us see what this sounds look like. So it's a music sound which some piano and drums are playing. So this file which we are going to work with. So how to load a audio file with Librosa? You just call a Librosa load function along with the file name. So what it will return is it will return like the frames of the file in numerical format, and the other one is sampling rate. Sampling rate is like standard here is 22,050. So how many samples have been sampled per minute? So that's it's in hertz. So now our main part. So when we said we are going to divide an audio signal into various acoustic components, what do we mean by that? So basically an audio file contains two main acoustic components. One is harmonic and the other one is percussive. So harmonic components are more like melodies or chords, like a piano playing or violin playing like in a soothing manner, which is kind of relaxing in a way. So these kind of sound, if you look into a spectrogram, which we are going to look later, more occur as a horizontal line. There are various examples which can be observed. So in real life you can find many variations of this as well. And the percussive sounds are more like a clash or a clap or click kind of a sound, more like a drum kind of a sound which beat happens suddenly, and similarly strokes as well. So that's the difference between both the sounds. Harmonic sounds are kind of a wave format, like a soothing kind of a sound, and percussive are more kind of a beat kind of a sound. So our aim is to segregate our signal into both the components. So for that we are going to use one of the libraries. Before that, let me give a reference. So this link, let me open into another tab. So basically there is a very nice explanation, and I have took most of the references from this page. So it explains the various thing and presentation that has been done, and I'll go behind that as well, like how they are separating these kinds of sounds. So you can look into that reference as well. The reference link will be present in the repeater notebook, which I will share later. So now, coming back onto a question into picture. So we are going to use the Librosa effects library, which is HPSS, which roughly stands for harmonic percussive sound separation. So what we need to do is we need to find the original wave format which we obtained earlier by loading the file, and it will do the rest. It will separate the sound into two wave format. One is harmonic and the other one is percussive. So it also take additional arguments but for this task we don't need them. You can look into it later by going to library. So now let us visualize how harmonic sounds look like. So as you can see, it contains only violin sound and not the drum beat sound. The other one, it is not shown here, but like I'll show you later that it contains drum beat sound and not that violin kind of sound. So let's go through the theory behind it, what exactly is happening here. What we are going to do is we are going to plot both of these sound waves and see how their spectrograms look like. So for that we are going to use short-term Fourier transform, which is present here, like Librosa dot short-term Fourier transform, and we need to pass the frames and the number of number of NFFT value and the Hopland overlapping part, and then we are going to use a hand window, which is by default, which is pretty standard. There are other windows available, but it is preferred to use hand window. Now, once we are going to run this, we are going to run the spectrogram, what we are going to see is these three kind of spectrograms. So, original spectrograms, as you can see, contain both vertical and horizontal line, whereas in the harmonic is more kind of a horizontal in nature, and the percussive more like a vertical lines separated here. So, this is what we talked about earlier, that this theory is exactly what we are going to use while separating our harmonic and percussive sound later. So what we are going to do is we are going to plot a spectrogram, and then we are going to filter the vertical and horizontal sound into a separate spectrogram, and then we are going to use inverse inverse algorithm to convert this spectrogram back into original sound. So this spectrogram, like harmonic one, will give us harmonic sound, and the percussive one will give us percussive sound. So let's look at let's look at some of the examples and see how it is working. So what we are going to do is we are going to load a couple of examples, and then we are going to convert these into harmonic and percussive representation as well, and then we are going to see how the output looks like. So let's go into the sound drums. Now it contains both the sound variation. Now let's go into this harmonic sound. It contains only melodies and nothing beats kind of a thing. And now if we go into a drum sound, let's see how it looks like. So you can see it's more kind of a beat kind of sound with certain noise coming in, but majorly it's kind of a beat in nature, and similarly like this. It's more clearer because the drums sounds are more clearer, and the harmonic sound is like this. The original should contain both kind of sound. So yes, so this is how the algorithm works, and I'm going to paste the link into the description. You can also refer to my GitHub page. In that I have an experimental repository, under which in the releasing section there's a audio section where I'm going to put all the audio related experiments.